All right, sorry about that. I forgot. Kind of went over time there. But so back to the problem we were working on before I got cut off. So we're using Charles' law. So we have to identify all of our variables first. So we have our T1 identified as 25 degrees Celsius. Our V1, so our initial volume is 2.5 liters. We do not know what our final temperature is, but we know that our final volume is 4.1 liters. So the very first thing we need to do, we need to make sure that all of our units are matching up. So we see that our initial volume is 2.5 liters. So we have liters for our initial volume, and our final volume is measured in liters as well. So we don't have to do any type of converting or bringing or making them the same. So we're good with those. So then we need to make sure, remember when we're dealing with Charles' law in this class, we want to make sure that our temperature is always measured in Kelvin. So our temperature in this problem was given to us in Celsius. So we have to turn it into Kelvin. Do you guys remember how to do that? Right. So you take in order to get Kelvin, you have to take whatever the temperature is in Celsius and you want to add 273 to it, and that will give us our Kelvin. So we'll take 25 because that's the degree Celsius we had, and we will add 273 to it. So our temperature in Kelvin, this is our initial temperature in Kelvin, is 289 Kelvin. Notice you don't have to say degree, it's just Kelvin. So, using Charles' law, which is V1 over T1 equals V2 over T2, and we're rewriting our equation, so now we have our Kelvin. So our initial volume is 2.5 liters. Our initial temperature is 289 Kelvin. Our initial volume is 4.1 liters, and we are solving for our T. So once we arrange all of that, you will have 2.5 liters that came from here times your final temperature, or our T2. It's going to equal 289 times 4.1. Then we're solving for our T2, so we're just dividing both sides by 2.5, and so we'll get that our T2 is 489 Kelvin or 490, whichever one. Either one will be fine. So then the next problem, try this one. What is the final volume of a gas that starts with 8.3 liters and 17 degrees Celsius, and it is heated to 96 degrees Celsius? So remember, we don't have to worry about our units because we only have 1 liters. We only have 1 volume, so it doesn't matter. But we are changing both of our Celsius into Kelvins. Remember, you do that by adding 273. We'll use this equation, our V1 divided by T1 equals V2 times T2. So that's going to break down because we are solving for V2. So that is going to be our T2 times our V1 equals our V2 times our T1. I may have just said that wrong. I'm not sure. I don't know what I just said. So anyway, you get an equation that looks like this. We are solving for V2, so we're going to divide both sides by 290, and so that you'll get that your V2 equals 11 liters. Problem 6, similar thing. So in this case, instead of our volume being in liters, our volume is in centimeters cubed, which is fine. That just means that our answer will be in centimeters cubed. So we have 225 centimeter cube volume of gas is collected at 57 degrees Celsius. What volume would this sample of gas occupy at standard temperature? In order to figure out standard temperature, you need to refer back to your reference table. It's the box that I showed you guys earlier in class. So we know we are trying to find V2 is the variable that we are trying to find. We need to change our initial temperature of 57 degrees Celsius. We need to convert that to Kelvin. So it'll turn into 330 Kelvin. And then here we go. We have our V1 is 225 centimeters cubed. Our T1, as I just said, is 330 Kelvin. And our T2, yes, our T2 is going to be 273 Kelvin because that is standard temperature Kelvin. Remember, standard temperature is going to be 0 degrees Celsius or 273 Kelvin. So solving for V2, this is how your equation should be rearranged. We'll divide both sides by 330 and we'll get that our answer is 186 centimeters cubed. So that is our final volume. Here's another equation. I'm not really going to walk you through this one. You just pause the video right here. And your final answer, your final temperature is going to be 161 Kelvin. All right, third law. Oh, long time. So this is Gay-Lussac's law. So this one is just stating that the pressure of a gas is directly proportional to the temperature if the volume is held constant. So in this particular equation, our volume is not going to change, but pressure and temperature are going to move together. So they are directly related. As one increases, the other one will increase as well. So this graph will look similar to the graph we talked about with Charles' law. We kind of covered this one in class, just talking about that as gases are heated, they will move faster. And that's what causes the pressure to go. All right, so here's our Gay-Lussac's law diagram. So once again, as pressure is increasing, so is our temperature. And remember to use Gay-Lussac's law, your volume must remain constant. So here's our equation. We have P1 over T1 is going to equal P2 over T2. You may notice all these equations are very basic. You just need to make sure you remember them. So for this equation, we have what is the pressure inside of a 0.25 liter can of deodorant that starts at 25 degrees Celsius. Then an atmosphere of 1.2 if the temperature is raised to 100 degrees Celsius. So in this case, the volume is remaining constant, and both before and after our final and our initial volumes are going to be 0.25 liters, but we see that our temperature is changing, so now we need to find what is our final pressure. So first thing, we need to make sure that all of our units for pressure are matching. We see that the only pressure unit we're given is atmosphere because we have to find the second pressure. So we're good on there. Don't have to worry about that. And then second, we need to make sure that we convert our temperatures to Kelvin. So we're starting out with 25 degrees Celsius. We need to turn that into Kelvin. Remember how to do that. We're just going to add 273. So that is going to become 200, I don't know what happened. It's going to be 298 Kelvin. And then our second one, we have 100 degrees Celsius. So we're going to move that to Kelvin. So what would that be in Kelvin? So it's going to be 100 plus 273. So it's going to be 373 Kelvin. So we're using this equation right here. All I did was mark out what our old temperatures were and put them in Kelvin. And so we know that our P1 is 1.2 atmospheres, our T1 is 289 Kelvin, P2 we are solving for, and our T2 is 373. So once again, we rearrange to solve for P2. So it's just going to be T2 times P1 divided by T1. And so our answer is going to be 1.5 atmospheres. Here's another question, another problem for you to take a crack at. I'm not really going to walk you through this one because I think by now you should kind of have the rhythm of it. All right, so now we're going to do the combined gas law. This equation, this is our fourth one, and this one is